Students, today I am going to teach you the relation between electric current and drift velocity. Last class I have derived what is drift velocity, relation between drift velocity and electric field, also with potential difference. Now let us establish a relation between, we can give the heading, relation between drift velocity and electric current. So it means VD, VD and I. What is the relation between them? So for that, let us consider conductor first. Let's say this is the conductor. Let's say its length is L. Let us write here L is length of the conductor, I is the current flowing through the conductor. Let's say A is the area of cross section of the conductor. Let's say N, this is called number density, means number of charge carrier per unit volume of the conductor. This is also called number density of a conductor. This N differs from material to material. Let's say Vd is the drift velocity. As you know, E is a charge on an electron. Charge on an electron. So these are the parameters involved here for the conductor current flow with a drift velocity. Suppose you have a conductor, across that a battery is connected. That battery is maintaining a potential difference of V across the conductor. Length of the conductor is L. Now you see the direction of the electric field is from this end to this end, means end A, let us take it to B. Let's say this end is B. So this battery is pouring down the electrons to this end. So electrons will flow in this direction and it will come here. So this is the direction of electronic flow in a circuit. So we can say the current is opposite to your electronic flow, which is like this. Let's say I is the current flowing through the conductor, means one electron will start from here and it will come to this end. So this is the direction of electronic flow, but this is the direction of current flow. It's a convention as already discussed earlier. Now suppose you see, let us, an electron is taking t time from here to here. Let us, an electron is taking t time from reaching the end A starting from B, means the length of the conductor is L. To cover that length L, an electron takes t time, that we can say. Let's say t is the time taken by an electron to move from B to A, means end B to end A. That's the time taken. Now let us understand what is the meaning of current here. We know the simple definition, I is equal to Q by T. All of you just understand, as the cross section area is A, it's not like that only one electron will flow from end B to end A. So when the potential difference is maintained, when the battery is connected, suddenly the current starts flowing and n number of electrons will start from end B to reach end A. So the total number of charge flowing from this end to this end, it would be, we can write, if the total number of charge, total number of electrons is n and charge on an electron is E, then the total charge will be n into E by T, it will be your current. Now let us understand this one, n. N is what? N is what? N is the total number of charge present inside this conductor. Why so? Try to understand. See, this is a continuous flow of current. As the electrons, as already I have told, one electron is taking T time from here to here, moving from end B to end A. So during that time, we are finding the amount of current. So between that time, what is the total number of charge crossing one cross section B? It means the entire charge which is present in the volume of the conductor, entire free charge that is present within this volume, they all have crossed this cross section and they have filled the entire volume of the conductor. Means this N represent the total number of electrons present inside this volume of this conductor considered. So simply N we can write this what? So which implies I is equal to this capital N will be small n. Small n means what? Number of charge carrier per unit volume of the conductor. Suppose in this volume, if you take a unit volume of it, n number of charge carriers are present. Just simple example. Cost of one chocolate is 5 rupees. Cost of 10 chocolates will be 10 into 5, 50 rupees. Similarly, here number of charge carrier per unit volume is n. Then total number of charge carrier present in the volume of the conductor will be n into volume of the conductor. Clear? So your n is a unit amount, volume of the conductor we can write n into volume of the conductor. Instead of this n writing this E divided by T. Try to understand this n is what? The number of charge carriers present inside this volume of the conductor. So that is small n means number of charge carrier per unit volume into volume of the conductor. N into this volume of the conductor is what? Area cross section into length. Area cross section into length into E divided by T. Got? Now according to the definition of drift velocity, if already we have mentioned here, T is the time taken by an electron to move from end B to end A. Means we know the speed at which an electron is moving from B to A, that is your drift speed, that is the average speed. And we know then according to using these 2 points, Vt and T, we can write the average length covered is L, the time taken is T, then your velocity, the magnitude of the velocity will be simply L by T, because already we are taking this term T, because T is the time taken by an electron to move from B to A, means the total length covered is L. So the speed, drift speed, the magnitude of the drift velocity Vd is given by the length divided by time taken, so which is L by T. Now you see L by T term is here. So instead of this L by T we can write here, which implies your I is equal to is N A, this L by T term will be Vd into E. So which implies we can simply write I is equal to A Vd N E. So So this is the relation between electric current and drift velocity. They are linked. And you see, number density is a factor here that decides, because this number density differs from, it depends on the nature of the material. Means, suppose copper is taken. For copper, N will be different. For aluminium, the value will be different. For your iron, the value will be different. Clear? Got? Now, from this equation, we can define another physical quantity. From this equation, we can define another physical quantity. Let us modify this equation and write here, like let us divide this term I upon A, which is given by Vd into N into E. This quantity I by A, it has a special importance here. I by A is what? In unitary method we can understand. Suppose here A is the cross section, you see this is the cross section A. If A is the cross section, in A cross section I amount of current is flowing. So per unit cross section, the amount of current that is flowing, it is I by A. This quantity is actually your another quantity that is called current density. Current density. This current density is a very important term. It will tell you, or it will give you the idea about how the charges, how the current is distributed over a cross section. This diagram is very simple, as it's a uniform cylindrical shape I have taken. So the cross section at each and every point must be same, must have the same value. So if the cross section is same, I by A value throughout the conductor has same value. But suppose there is a conductor having variable cross section. Somewhere the cross section will be like variable cross section. So if I can take a variable cross section like this, we will say here, this will be the same. So in that conductor, this is a conductor, and this conducting body is connected to a battery. Then what will be the amount of current flowing through the circuit? See, as the current is a continuous quantity, the value is fixed for the entire circuit. Because the battery is maintained a constant potential difference across this conductor, so the value of the current in the circuit is has the same value. So then what is the difference in taking two different geometrical objects? One having a variable cross sectional area and the other one is having a uniform cross sectional area. So there the term of current density plays a role. Here you see that as the cross section area is small, so the charge when they flowing, they will be just separated. Clear? And here they will be again reunited, means there is a constriction part, area is less here. So the current density is here, means we can say as the area is more here, means area more means current density will be less. So here the current density has a greater value in comparison to that of this area. So this is the quantity that distinguished how the current is distributed over the cross section. This is a vector quantity. This vector quantity is defined in this way, like, so we can write here J is equal to Vt into N into E. J is equal to Vd into N into E. The vector quantity J is, we can write your I is equal to J into A. See, J is a vector quantity, area can be treated as a vector quantity. So their dot product will give you the current in the circuit, current through a cross section. Clear? So this is the most important point here. Clear? Now let us derive the Ohm's law. Let us derive the Ohm's law from this relation I is equal to AVD NE. We can derive Ohm's law here, see, we know Vd is given by E tau by m. So this, the other form is, which is E V tau by m into L, where E is V by L. Now the second point we know, I is equal to A into Vd into N into E. Now we can substitute for Vd here. Vd, we can take this value and put it here, which implies I is equal to A into Vd. Vd is what? E V tau by m into L into N into E. So this Vd I have just substituted from here. Now you see, which implies I is equal to A, see here, into N into E square into tau by m into L into V. Now we can write V is equal to m into L by n e square tau by A into I. Got? You see here, for a particular value of a length of a conductor and fixed cross-sectional area, m is the mass of the electron here, n is the number density, E is the charge on an electron, tau is the relaxation time. So you see this quantity, it depends upon the nature of the material. Out of this m and E, they are fixed for any kind of material. But this n and tau, it depends on the nature of the material. Means n and tau, it depends. Nature of the material means for copper, it is different. For your aluminium, it is different. So this quantity, this term, we can write here, V is equal to, that quantity is called your resistivity into L by A into I. So which implies V is equal to, see, for a particular geometry, means for a conductor having a fixed length and fixed cross-sectional area, this quantity is a constant. So it is equal to R into I. So we can derive Ohm's law from this relationship. I is equal to AVD NE. This can be asked in your exam. Got? So here another derivation is also asked. Sometimes what is the relation between J, means current density, and your electric field? That you can simply substitute Vd is equal to E tau by m, and this equation you see current density is J is equal to Vd into Ne, that we can write here. So we can write here relation between J, means J vector, and electric field. Got? We know Vd is equal to minus E tau by m into E. Okay? And we can write here, which implies also another equation, that J is equal to Vd, J vector is equal to Vd into N into E here. This equation is actually, we have, if you take the sign of the charge, we can take minus E over here, or simply we can write, which implies J vector is equal to, instead of Vt we can write E tau by M into E vector into N into E. So which implies J vector is equal to, you take the sign of an electron charge as minus, so it is minus minus plus, so which is equal to N E square tau by M into E, and this quantity is called your conductivity sigma. So here sigma is equal to N E square tau by M, which is the reciprocal of, means resistivity, or resistivity is the reciprocal of conductivity, which is M by N E square tau. This equation is relating your electric field and current density with the conductivity. So this is otherwise called the vector form of your Ohm's law. Now let us understand a very small term here, that is called the mobility. These are the terms you must know to know the current electricity. Clear? Mobility. Suppose there is a conductor, and in that conductor you are applying electric field E, and the drift velocity you found it to be Vd. You are applying, the strength of the electric field is E, and you observe that the drift velocity of the charge carrier inside that conductor is Vd. So per unit electric field, means if the electric field would have been unity, means per 1 unit your drift velocity would be Vd upon E. This quantity represents your drift velocity per unit electric field. This is called drift velocity per unit electric field. This quantity is called mobility, and the symbol is mu. Mu is equal to Vd upon E. So we can write here Vd is what? For an electron, if you take the magnitude here, E tau by M divided by E. E got cancelled, so which implies mu is equal to E tau by M. This formula, the drift velocity, mobility for an electron. In terms of, if you take any charge, for any other charge, the mobility will be what? Drift velocity of that charge divided by electric field. So in that case, you can replace this E with your Q. So in general, mobility will be what? Q tau by M. This is in general. But here, this formula, it is basically for your electron, my dear students. That day we have discussed, or we have plotted 3 different varieties of graphs with a variation of resistivity with temperature. We have plotted a graph between resistivity with the temperature for conductor, semiconductors and insulators. That day I have told you I will explain the reason in latter part. So to understand the reason, the derivation what I have done today, that you need to know. The resistivity, the formula of resistivity we have derived, rho is equal to M by N E square tau. Clear? Rho is equal to M by N E square tau. This term you must know. Rho is the resistivity, M is the mass of an electron, E is the charge on an electron, N is the number density, and tau is the relaxation time. Already I have told you that M and E is fixed for every material. N and tau, it depends on the nature of the material. For conductor, we have plotted the graph like this. Hence, resistivity with the temperature, it increases. With the increase in temperature, the resistivity increases. Why? Try to understand. For conductor, we have large number of free electrons. If we increase the temperature, try to understand, since there are a saturated number of free electrons present inside a conductor, the value of N, the number density, won't change appreciably. Got? So if you increase the temperature, the atom may not release extra number of electrons, as there is a sufficient number of electrons present. Clear? Or at very high temperatures, this value also changes. And so, the value of N won't affect the resistivity to a greater extent. It affects, but its effect is very less in the case of your conductor. Let us come to this relaxation time. So, if you increase the temperature, the thermal motion of all the electrons, it increases. Thermal motion of electron increases. Means, suppose one electron is moving from this point to this point and it gets collided. So that is the concept of resistance. So with the increase in temperature, as their thermal speed increases, so this gap is covered very rapidly. This is the gap between two successive collisions. So the time taken by an electron to reach from this point to this point is the relaxation time. So if you increase the temperature, the random motion of the electron increases, so their thermal speed increases, and the collision time, that is called relaxation time. Relaxation time means the time gap between two successive collisions, it decreases. So if the value of tau decreases, this value of rho, it increases, because rho and tau, they are inversely proportional here. Clear? So in the case of your conductor, T increases, but if T will increase, tau will decrease. If the relaxation time decreases, then as resistivity is inversely proportional to your relaxation time, since tau decreases, your resistivity increases. This is the cause. That's why if you plot a graph, the graph will be like this. But in the case of your semiconductor and insulator, this is the case of your conductor. But for semiconductor and insulator, semiconductor or insulator, with the increase in temperature, semiconductor and insulators, they do not have any charge carriers, free electrons. So if you increase, there is no current charge carriers present inside that material. If you increase the temperature, the value of N increases. Clear? The value of N means the number density of the charge carrier, it increases. The relaxation time, it does not affect to that extent. It is affected, but it's a very lesser amount this will be affected. So here the relaxation time's effect cannot be considered. It won't change appreciably. So in comparison to the change in the number density, this relaxation time has no effect. So we can neglect the effect of relaxation time. So in the case of semiconductor and insulator, that increase in temperature, the number density increases. So here N means we can write, if T increases, N increases. But rho is what? It is inversely proportional to n. So if n will increase, this rho will decreases. Means the resistivity decreases. So this is the graph of your conductor. So for a semiconductor and insulator, the resistivity versus time graph will be like this. So this is the explanation of these two graphs. This can be asked in your exam, like write the reason why or explain the variation of resistive temperature for conductor and your semiconductor on this theory. So you need to start your explanation from this equation. Clear? Thank you.